My name is Jenett Tillotson. I'm the Senior Cluster System Administrator at Indiana University. I work for the Research Technologies group. We do all of the research computing for the university in my group. Oh, sorry. I have to do it. Is that better? Yes. All right, my name is Jenett Tillotson. I work for I'm a Senior Cluster System Administrator at Indiana University. I work for Research Technologies, and we do all of the research computing for the university. And so I'm just going to kind of give you an overview of what we have going on at IU and how we use Moab to basically give access to our resources. So we have our big flagship machine is Big Red. It's a 1,024 node JS21 IBM Blade Center. It has two dual-core PowerPC 970s in them, 8 gigs of memory per node. We have a 1-to-1, 2 gigabit MirrorNet interconnect, so it's not oversubscribed at all. And on it, we run Load Leveler on that because it's an IBM machine, and we run Moab as a scheduler. And then Quarry, which is it's a kind of it's a very heterogeneous system, which I would not recommend. Heterogeneity is a bad thing. Anyway, it's got a 140 node IBM HS21 Blade Center. So that's 2 quad-core Xeon 335s, and they either have 8 or 16 gigabytes of memory. So we have some what we call high mem nodes. We also and it has 10 gigabit Ethernet as its interconnect, and that's oversubscribed. We also have 230 node IBM iDataplex. They're DX340s. They have 2 quad-core Xeon E5410s in them, 16 gigabytes of memory in each one, and they're only using 1 gigabit for the interconnect on those nodes. So it's like these two disparate systems, iDataplex and a Blade Center. We like the name Quarry. I think that's what it comes down to. I think we want to name everything Quarry. So, but this is all under one resource manager and one scheduler. And that one runs Torque and Moab. And then there's Mason, which is our high memory machine. This is an HP system. It's got 16 nodes. They're DL580s. So there's 4 8-core Xeon L7555s in them. And 512 gigabytes per node of memory. And it uses 10 gigabit Ethernet for its interconnect. And it also runs Torque and Moab. I'll talk a lot more about Mason later on. There's some very interesting scheduling challenges. All right, so just to give you an idea of what our user base is like at IU, we are an academic institution. We have, 30,000 staff and students, maybe more. And we provide access to the supercomputers to everyone. It's free, and it's just a simple click of a button to get an account. It takes 15 minutes. You can run on the supercomputer. What this means is you see a really large, very disparate user group. So we have people mostly, of course, these are logins over the last 15 months. So a lot of staff logins, of course, but then physics, chemistry, informatics. We have some generic students and faculty that aren't actually in a particular group. But then you also see, business. You see linguistics, the library. So we have a very disparate user group, and we don't favor any user group over any other user group. If you look at my jobs, now this is just my pure jobs. So informatics, which is our computer science department and other things along those lines, they're a huge piece of that pie, but they run a lot of serial jobs, and that's what this is comprised of. And these are all on Big Red, by the way. So this is just individual jobs. It doesn't really say how much CPU time they use or how much of the cluster they use. We're just looking at jobs. But again, we get them from all over. To really understand the cluster and how it's being used, it'd be great to have also by CPU, but I'm not going to go into a lot of detail. I don't have much time. So our queuing systems on Quarry and Big Red, you'll see these long and normal. These are our two main queues that we use in our clusters. They're named this because it's the TeraGrid naming scheme. These are the TeraGrid queues. If everybody's heard of the TeraGrid, it's a NSF project to hook together these big supercomputers that are NSF funded by Big Network and then give an allocation system so that researchers at institutions, NSF-funded institutions, can get access to supercomputers. And they call their queues long and normal, so we call our queues long and normal. And that's now, that Tergrid grant is now ended, it's now at C, if anybody wants to go look it up, XSE. Anyway, so we have long and normal. Long is fewer nodes per job, but longer wall clock times. And normal is more nodes per job and shorter wall clock times. And I really don't know why Corey, I'm not the Corey, I'm a big red admin. I don't know why they only allow 6 nodes on their normal job. I didn't get a chance to ask them for this slide. But for Big Red, you really see this small number of nodes, but long wall clock times, large number of nodes, short wall clock time. And this really reflects how we expect the cluster to be used. So we want to see big jobs, so we actually partition the cluster, not assign some nodes to the normal queue and some nodes to the long queue, so that these two are separate, and the long queue doesn't affect the normal queue and vice versa. For people to run these large jobs, especially on Big Red, we have this not oversubscribed interconnect. And then serial queue is usually defined on Big Red. It is every node is in the serial queue. So backfill. That allows us to stick individual jobs anywhere in the cluster where there's a hole. And you'll see those are short and small number of nodes. So this is how we get a cluster. We also have the debug queue, which is just a really short, dedicated nodes to that debug queue. And it's a short turnaround. That's for 15 minutes of wall clock time. So you can just really use it to test your job submission, really, is what it's for, and that your job starts. On Quarry, it's only on Quarry with those high-mem job, or those high. And that one, I think you have to actually specifically request the high-mem nodes. Leveler, it's all very specific and assigned. Queues are, like these nodes are long nodes, these nodes are normal nodes, and you have to pick one of those queues to support with Torque. We use a routing queue for the most part. Most users just rely on job into the right queue, but the high-mem queue, so it doesn't, it's not routed. As this cluster, how do we make sure that all users have access? It helps this machine as all professors or all faculty members. They use it to recruit faculty members. So how are we going to make sure that every faculty has a chance at the queue, or at the cluster that the other faculty member has? And what we do is our fair share. So we try to give every user 5% of their cluster, our target. And once a user gets it, their priority will start to go down. But until they've reached that 5%, they have the same priority. But as soon as they reach that 5%, then they start to move down. So this allows users who are coming for time, or maybe haven't used the cluster in many months, to come in and immediately start to run, or at least as opposed to people who are really utilizing the cluster. Really how we allow this kind of broad user base to get access. The other thing we do factor in is X factor, which is, of course, this ratio of wall clock time to how much you've been waiting in the. So you don't want a job that's only got a day of wall clock time to wait a month. The ratio, and I can't remember, it's like 2.5, it's typically set to by default up of your wait time, you'll start to move up in the queue. But we also wait. So if you ask for a large number of processors, we'll bump you because we want Big Red to be utilized as a big parallel machine. But it's very, and this line up here, is your friend. So on your own cluster to see what your priorities of all your jobs. Then we do some other things. One user. And so we make sure that they don't queue stuff. So if they do submit jobs into the cluster, we only give to the first 16. So the rest are blocked by Moab, and so they won't accrue priority by wait time. Right? Only the first 16 jobs they submit will get that priority. We'll gather wait time on that. Once those 16 jobs are run, the next 16 jobs can move in, and then they'll accumulate priority too. And this keeps filling the cluster with jobs and then getting the entire cluster. We also limit nodes per user, of course. One user, a certain number of nodes in each queue. And we also limit the number of jobs that they're able to submit to the resource manager. This is mostly just so that it doesn't overwhelm the resource So we have I think it's set at 512 maybe right now, of how many jobs any one user can submit. Once they've submitted that much, the resource manager will actually stop them and lock them. And then one of the things that we do use quite a bit, rather than reservations, so let's say a user wants, they have a big grant due, we get this all the time, they need some jobs run in a month, and so we need to give them priority on the cluster. Rather than reserve them a set of nodes, give those nodes to them for a month and let them utilize it, what we found is they wouldn't utilize the nodes. Those nodes would sit idle, more than they would be run. So more than 50% they would be idle. And again, for a cluster widely used and supposed to be heavily utilized by all users, watching these nodes sit idle was kind of frustrating. So what we do instead is we use the QoS facility. So what we do there, we basically define a QoS, put a user, we say how many nodes that they can have in that QoS, and then bump their priority up a bunch, 50,000. We add the maximum to their job. So when they submit, they have to say that they're submitting to the QoS. They have to tell this belongs to, or actually it's in Moab, that this belongs to this QoS. Put it on. When they do that, they will then get to the top of the queue. They'll basically get next to run status. And then once nodes become free, they'll get them. And then can keep those nodes as long as they keep jobs in the queue, and they'll continue to run. They could run forever until their jobs are no longer in the queue, until they have quit. Then those nodes will go back and people can run on them who do have jobs in the queue. And this really helps our utilization. And the idea too, not being nodes, improves the wait time for the QoS. And then the last thing, I'm going to cut this short so Michael has more time, is our Mason cluster. So this large memory cluster, 512 gigabytes of memory, it really has created some issues for us. The first issue is that we have 16 nodes. 12 of them are supposed to be for a genomics project. So they're just for doing genomics. The genomics users have this need for large amounts of memory. And then 4 nodes are for any generic IU user. So we have this kind of and we're having a really hard time figuring out a way to map. Again, a large number of users we have on Big Red at any given time. There's 300 active users on the cluster. So we're struggling right now finding a way to map, a large number of users and maybe incoming users onto these 2 different sets of nodes. We'd love to do it with Unix groups, but it's all, as far as we can tell from Moab, it's only based on the primary Unix group. And so, of course, there are all of these different other Unix groups. They're in informatics, they're in physics, they're in chemistry. And so it would be great if we could define a genomics group and a non-genomics group and work, but we don't get secondary groups in Moab yet. At least nothing we've found. Then the second thing is that I think this is coming up. It does look like maybe not this next release, the next release of Moab, the release after that. There may be a way to do these kind of particular bank of memory. That way we could have these nodes shared. So we could have multiple users, but the schedule more based on processors or cores would be really nice. And we're trying to figure out a way to do that. So that's like, and the idea of like restricted memory. If a user comes outside of their memory, then we kill the job, even though the node's not out of memory. So that's our Mason cube or Mason cluster, sorry. And that's all I have. So does anybody have any questions?